Hey everybody, I wanted to follow up with our discussion board about worksheet 1, problem number 3, and try to figure out what to do about downward acceleration in our free body diagrams. Where was that discussion board? We had a photo. Of course, I don't have the photo anymore. Oh, there it was. We're just kind of discussing this, and I know the person feels like, oh my God, my work is up there. But it was so neat. And it had some stuff that was important to discern. There were two things that came out, which was fantastic in your discussion board, and I love it. Okay, first of all, we noticed the tick marks. It's really natural to say that force normal and force gravity are equal to each other, right? But if there's acceleration upwards or downwards, they can't be equal. Okay, so we have to discern, is one going to be greater? Which one's greater than the other? The others we forgot to label. And the last thing people caught was about the acceleration, right? The calculation came out correct, I believe. Did it? Nope, calculation came out incorrect, so we need to kind of look at that. So what I thought I would do is put it up on the board and just talk about a few steps as we go through, okay? Sometimes steps can help. I'm going to put this up and see if we can work through it, okay? First of all, we got our work. My mass, it was not 80. It was 85 kilograms. Oops, had some caffeine this morning. My hands are shaky. So 85 kilograms, and then the acceleration was 3 meters per second, or 3 meters per second squared downward. So whenever I've got acceleration, it means my forces are imbalanced, okay? Now, while I can do my free body diagram, the first step always, one, free body diagram, okay? That's your first step. When we're in a place with acceleration, we need to note which way that acceleration is. And so downward, right? 3 meters per second squared downward. Now, I like quantitative force diagrams, but if I know it's downward, right, conceptually, what do I know about the forces? Which force is greater than the other, right? So if it's downward, that means the net force is downward, right? So concept-wise, right, force gravity is greater than force normal, okay? That's the concept. I always like to briefly, like, in my brain, think which one's going to be greater. Now, force gravity, this person is just standing in an elevator. Their force gravity doesn't change, so we take 10, right, newtons per kilogram times 85, and we get 850 newtons, okay? So this won't change. The only time this changes, right, is immediately, like chopping off a leg. That's bad. Or over a long period of time, say after Thanksgiving and Christmas, and then you add those kilograms. But this is a scenario where you're not doing that. They're staying the same. So force normal has to change, which means, if you remember, I had folks go on the elevator and stand on the scale, right? Or you've been on an elevator and you've felt this. If the acceleration is down, so let's say our movement is upward and our acceleration is downward, meaning you're slowing down, you feel lighter on the elevator, meaning that scale reading will be less than what you would normally be, okay? So that's kind of the concept. All right, so that's step one. Step one is for free body diagram, and then I put some quantities on there, and I put the direction of acceleration, okay? 2, frame of reference. Establish your frame of reference. What do you want up to be? Do you want up to be positive, which is normal, or do you want down to be positive? I could do this whole problem with down as positive. You would hate it, but you can do it, okay? So frame of reference, now I usually do frame of reference where I say positive is up. That's usually what I do, okay? So up Positive, down would be negative, okay? So what's that do? That means force normal is positive, acceleration is negative, and force gravity is negative, okay? So the third step, right, is the force net equals mass times acceleration, and this right here is from the free body diagram, okay? So this is, put it into Newton's second law, force net equals mass times acceleration, and get this from the free body diagram. So what's my force net? Right, and they asked you that in most of the problems prior to that. Well, I've got a positive force normal, I've got a negative force gravity, I've got a mass, and I've got an acceleration. Okay, now I could put, just to be clear, a negative acceleration. So I've got force normal, I'm trying to find force normal, I don't know it, minus the 850, right? Mass was 85, and what was our acceleration? 3, so negative 3. So when I do this, oh gosh, I don't even know what 3 times 85 is. I could do math in my head, or not. 85 times 3, right? That's a negative 255, right? And then I've got force normal. If I add 850, so plus 850, guess what happens? Mathematically, it matches with our work, where 850 minus 255 equals 595 newtons. So if I were standing on a scale, if I go at constant speed, it's 850, 850. The forces are balanced. But if I start to, my velocity is upward, but my acceleration is downward, meaning I'm slowing down, a negative, right, acceleration, I get it chipped away from my original weight or force due to gravity. The scale is going to read lighter, okay? So first step, free body diagram, but let's note the acceleration. Let me put that in a different color. Indicate right, so let's do the free body diagram, indicate the direction of the acceleration, establish your frame of reference. Up is positive, okay? And then 3, force net, put it into Newton's second law, force net equals mass times acceleration. This is from the free body diagram. Positive force normal, negative force gravity. And then this is your data, right? Mass, that's scalar, always going to be positive. And then a negative acceleration, a downward acceleration, or a negative 3. And then that should make through most of your free body diagrams. Okay? I hope that helps.